QA inspection manager on special considerations when repairing FRP tanks. So if you missed that one and would like to watch that one, reach out to us and we'll give you the link for that. Today's topic, we're going to talk a little bit more technical. We're talking about FRP system analysis and pipe support selection to ensure reliability. So let's get started. Okay, I think you should know a little bit about me so you understand a little bit where I come from and some of my credentials. I've been with Maverick since 2006, going on 14 years here. I'm now the engineering manager of Maverick. And so just some of what we do at Maverick with our engineering capabilities, we do pipe stress analysis, equipment design, FEA. We develop project specifications, owner specifications, specifically for non-metallics. A lot of owners don't have those in-house, so we assist owners with that. I manage the pipe support division as well, so we do have our own line of custom pipe supports specifically intended for FRP and thermoplastic piping. Some of our other engineering responsibilities also include acting as the owner's liaison for assistance. So we assist with bid reviews, calculation reviews, design reviews to make sure that they meet the specs, meet all relevant industry codes and standards. Owners don't always have those technical subject matter experts in-house, so we act as owners' representatives in those instances. I'm an active member of a couple groups with ASME, the design subcommittee for RTP1 for FRP atmospheric vessels, plus or minus 15 PSIG, and I'm currently the vice chair of the new NPPS NM2 FRP pressure piping design subgroup. That is certainly a mouthful. I will mention NM2 and NM3 throughout this presentation, so I'll explain a little bit briefly what that is in upcoming slides. A little housekeeping here. We highly encourage questions. I expect to talk for about 40 to 45 minutes and then we'll answer questions the rest of the time. In order to ask questions, your panel won't look exactly like what you see on the screen here. I can assure you all questions are private. There is no chat function. All of your questions are going straight to Tom, who is gathering them. So that way we can kind of compile everybody's questions into similar questions and make sure we can get through as many questions and provide as many decent answers as I can provide. You also see slide numbers at the bottom right of the screen. So if you need to reference a slide, that might be helpful. There's a lot to discuss here, so it's going to be fast and furious. I tend to talk fast. I don't strictly read my slides, so just kind of keep that in mind as we go forward. This will be available afterwards, so maybe you could read the slide, you can request the presentation, or you'll be able to watch the webinar again if it goes a little too fast, but there's just a lot of information to convey. Having said all this, just keep these expectations in mind as you're going through and as you ask your questions. In my mind, if you can identify all of these expectations, or at least kind of understand some, or have some understanding of them, then I feel like I did my job. So I'm expecting the attendees to be able to understand that construction methods vary and ultimately affect material properties with FRP. You should know that some of the primary differences between analyzing steel and FRP. I expect that's a fair amount of the attendees here have a good experience with steel, maybe not so with FRP. You should be able to identify different analysis approaches based on what system routing you're given and what kind of design conditions you have as well, whether it's high temperature, low temperature, high pressure. You should understand some of the gaps between theory and reality. That's a very big gap. Is everything looks great inside a computer, and when it's operating in real life, theory is not always reality, and the analyst is responsible for overcoming that. Finally, you should know what separates appropriate from inappropriate supports. That'll be the end of the presentation here. Now, I do not expect to teach the attendees to learn how to use Caesar. Caesar is a pipe stress software. It's basically the Cadillac, we say, so I will be referring to Caesar throughout. I'm not going to teach you how to learn Caesar. I'm not going to teach you how to do pipe stress for FRP. That's not the goal of this presentation. So any kind of questions related to Caesar configurations or modeling questions specifically related to how different pipe stress softwares do it, probably won't answer those. It doesn't mean I can't talk about it offline, but it's not something I hope to kind of educate in this webinar. So my assumption is that most attendees know what pipe stress analysis refers to. But for those who aren't familiar, I want to establish this so we're all on the same page for this webinar. So throughout the webinar, just so you know, I'm going to refer to pipe stress, PSA, and Caesar. It's all kind of interchangeable. So just kind of understand that. So what is pipe stress analysis? Pipe stress analysis, it's a calculation method to predict combined axial stresses in piping and loads on supports and equipment. It's an iterative solution technique to help optimize the most efficient pipe routing, dimensional requirements, support locations, and types. The program does not do everything for you. It's just quicker than doing it by hand like they did 50 years ago. The analyst still needs to add all the inputs, do the routing, material properties, figure out support locations, and iterate on their own. It's still a very manual process. It's not, you don't just plug it in the computer and have it do it for you. But why is pipe stress important? And specifically for me, and for what I'm going to talk about here, is why is it needed for FRP? For FRP, it's a non-ductile failure mode. You don't have any warning. So you need to be certain of the stresses within your system, the displacements within your system, and make sure everything is properly managed. So we'll first go through things to be considered. This is not a unique approach, not just FRP, but being aware of these considerations and how FRP kind of relates to these different aspects prevents oversights from happening. So you need to understand the product, you need to know about the material that you're inputting, understand system geometry, design conditions, and finally we'll talk about load cases and combinations. I'm going to talk more about thermal expansion and low modulus here in future slides. As far as the material, so you have to understand there's different construction methods. You can't assume one construction method or one customer's product line. Pressure ratings can be different, thicknesses can change, stiffness changes, properties changes, allowable stresses change. It's not one size fits all. With a joining method, whether it's butt wrap, socket adhesive, if you don't understand what these are completely, I don't have slides specifically what these joining methods are. I'd be happy to field questions on those later or after the webinar. But the joining method matters. Socket adhesive are very quick to assemble, but they're not as good in bending. There are currently no weld efficiency factors for FRP. I can say that Maverick is currently working on it through an ASME project, but we're not there yet. So you have to understand the joint system and how that can affect the hotspots in your system. SIF's stress intensification factors and flexibility factors. I know Caesar has modules for calculating these. We recommend to calculate them specifically for your product that you are analyzing. I do not recommend using stock properties for SIFs or Ks. Construction method matters, thickness matters, properties change the SIFs, whether it's mitered elbows or smooth sweep elbows, and analysts familiar with Caesar or any stress analysis software will note that there are axial and hoop direction SIFs, and which one you use is actually dependent on which type, or which one you should use, I'll say that, is dependent on which type of elbow you actually have in your system. And physical properties and allowable stresses are later slides because I know allowable stresses are a hot topic among those who are watching. Just a very quick background, just so you know a little bit of what I'm talking about here, just if you don't have the FRP background. When I mention type 1 laminate, that means it's only constructive layers of chop strand mat. It's very high resin content, about 70%, which means 30% glass content. Type 2 means alternating layers of mat and woven roving. That's the picture on the left there is a woven roving. This has slightly higher glass content at about 40%. And then type 3 is kind of a new designation in our new standards, but it's basically 55-degree film and wound pipe, very optimal wind angle. This is the strongest, it's the most controlled, so it's about, I would say, 60 to 65% glass. I'm not going to dwell too much on this slide. Just understand that one of the main differences is steel is isotropic, meaning properties are the same in all directions. FRP is orthotropic and it can be customized, which is a great benefit of FRP. But that means the properties vary depending on the resin, the glass, the laminate sequence used, the angle that you're winding. So properties vary. You can determine each of these by two ways. Really material testing, where you just destructively test. You see the different ASTM methods that are displayed there. There are pros and cons to each. Or you can just do theoretical by laminate analysis, that there is commercially available software available, or any real ASME FRP standard also has methods. So in talking about tensile modulus, you see kind of the wave in this graph. So the value on the way right is a Caesar default. If you don't know anything about FRP and you just know you have to analyze FRP, you might just use 3.2 million modulus. Still a lot more flexible than steel, but compare it with 8 other product lines. If you just go online and look at different fabricators and their product lines, they advertise these different modulus values. So which one is right for your system? You can't just plug whichever one you want, because a lower modulus means it's more flexible, means it's more forgiving, which could also be unconservative. If you use stiffer, you think you can go longer spans than you really can. I'm going to take this time to just briefly introduce NM2 and NM3 that I've been talking about previously. I'm not going to go to deep extent about this. There are plenty of ASME webinars out there. It's a new pressure piping standard they're great webinars given by very technical people that explains it very well. We may do a webinar in the future on it as well. Basically, for what the viewers need to know is there is some of the gap filled with NM2 and NM3, where there are stock properties in NM3 for FRP type 1, type 2, and type 3 laminates. So you don't have to do all of this guesswork. You can just use a stock value, but it will be conservative. And that also goes for allowable stresses too. So people would be happy to note that there are allowable stresses published in NM3. Thermal expansion. This is a very big deal for FRP compared with steel. The bar on the left is for type 1. So the resin is what expands. So you'd expect type 1, most resin content, to expand the most. So it's important to note here, you have 3 different construction methods and 3 different thermal expansion coefficients. So it's crucial to know which one you are using in your analysis. The main takeaway from this is obviously the coefficient of thermal expansion change between products for FRP, but also compared to steel. Just looking at carbon steel, you're anywhere about 2 to 3 times that of what steel is. So here's a general example. When we see systems operating at 160 in the FRP industry, to me that's an elevated temp. To somebody familiar with steel, they think 160 is pretty low. So we just do a quick example here of a 100-foot length of pipe based on a delta T of 90, 70 off of the installation, or 70 degrees is the installation temperature. You get a growth of almost 1 3/4 inches in that system. To get 1 3/4 inches of growth for a steel system, that's the equivalent of a design temp of 305. So when you present a 305 degree Fahrenheit design temperature for analysts, steel analysts, then they start to think their system is a little bit more sensitive and might need a formal stress analysis. The other big item to talk about with FRP and why it's crucial to analyze and why it's important to understand what you're dealing with FRP. It's a non-ductile material. You can hear that as brittle if you want. Brittle doesn't sound good, so us FRP guys say it's non-ductile. But you can see with these elongations here why it's so critical to manage stress in FRP. There's very little warning if FRP breaks. So you need to stay within that box of allowable stresses. And you need to make sure when you're adding temperature to your system that you're not treating that like an expansion case as you would with steel, because steel can locally yield and it relaxes a little bit. FRP, if it gets to that point, now you have failures, which tends to look like this. Now, it's always nice for us to get a failure in action. It's a great picture, not so much for the owners. Frankly, some owners deal with this too much. We're constantly dealing with failures, repair procedures, or going into plants and seeing overwrap joints, understanding that they've had issues with those locations previously. It's unfortunate, and I would say it's unnecessary because we know a lot more now. We know a lot more than we did 15, 20, 30 years ago. We have good standards in place. It's a science. But these failures happen when displacements and stresses just aren't properly managed. Getting back into the considerations here, just talking about geometry, you need to understand what's the routing, how flexible is it? I have later slides kind of comparing a few different systems, a few different common analysis methods for FRP systems based on how flexible they are. Where are your inline components and how heavy are they? Spans may need to be shortened if you have heavy inline equipment. Where are existing supports? Do you know of any locations of available steel if you need additional supports? If you're replacing an FRP or a steel line with FRP, then the spans are probably a little bit longer, so you're going to need to identify intermediate steel. Take note of any stiffer locations. You want to put anchors really at your stiffest locations to be able to be the stiffest and handle the reactions imposed, and it's not flexing while it's operating. And then finally, understand the connections. Are you connecting to a pump? Are you connecting to a steel tank, an FRP tank? What are the stiffnesses of those connections? Are they rigid? If it's an FRP scrubber vessel, you might have a nozzle that's 50 foot in the air. If that vessel is operating at 200 F, 50 foot in the air, you can bet it's growing a fair amount. So you need to include that initial displacement as well. The design conditions ultimately affect the complexity analysis. It's not just the routing. Conservative assumptions will affect the cost. It's important to note, and this is clear in NM2 now, that when you define or when you see pressure and temperature, you need to analyze at the operating pressure and temperature, not the design. It's pretty common for specs to just say 150 psi, 200 F, but that's more pressure rating and resin selection. That is not the operating conditions. It will hurt your system. It'll make it more expensive. It'll be more difficult to analyze if you have a system that literally cannot operate at greater than 70 psi, but you're analyzing it at 150. I'm not going to talk too much about surge analysis and dynamics. Surge analysis is not common in our world. If you have a worst case surge event, you're going to blow up your FRP pipe. The operators need to implement engineering controls to be able to reduce surge to as little as possible. There are fundamental support layout guidelines, and including anchors in each change in direction, which help to mitigate any minor surges. What I'm showing here are recommended minimum load combinations. There are more, and it depends on what your system is. I always say dead weight plus pressure is a very good place to start. If you have elevated stress in this case, adding temperature certainly will not help your system. It's not going to make it lower stressed. So higher stress and dead weight plus pressure tells you might need supports, more supports. Maybe your spans are too long. Maybe you need a support in your riser piping somewhere. It's crucial to show here that temperature is a sustained case. It is not an expansion case. $1 million question here. What is the allowable stress for my FRP piping system? Well, I've probably said it a few times here. There's no one size fits all answer, although I will say, and I'll repeat, that NM3 now provides guidance, but it will be a conservative position. I'm not going to go into all of how NM2 and NM3 define allowable stresses, but just know that there is something there. But before NM2 and NM3 existed, we would have to select our allowable stress based on construction method. It changes, type 1, 2, 3, or custom, it changes. What is your loading? Do you have expansion joints in your systems, or is it bidirectionally loaded? That affects the stresses in the pipe. What kind of material testing has been performed? How confident are you in the ultimates? And what are the service and fluid conditions? You might be a little bit more concerned if you have HCl going through your pipe, or chlorine dioxide, or wet chlorine versus seawater. For steel, however, depending on the fatigue factor, you can have a displacement stress range allowable increase of greater than 100% just for thermal loadings. For FRP, and this is only recently, before NM2 came out, it was 0. But with NM2, we have now allowed 10% increase in allowable stress when you analyze dead weight plus pressure plus temperature. So it is not just for a thermal case, it is for what we call a sustained case of dead weight, pressure, and temperature. Showing another graph here of the variability you'll get between different manufacturers and construction methods for ultimate strengths. It's all over the map. And Caesar, as it should, doesn't give a stock value, which I know drives a lot of you guys nuts because we get that question fairly often. And I know fabricators and manufacturers get those questions as well. Now, after seeing these, how confident are you that you know what the allowable stress should be if you're not familiar with each of these products? Well, this is what can happen. If you overestimate the allowable because of unknown product, you could have a stiffer product, more flexible, stronger, weaker. If you include an expansion stress allowable as a secondary stress, not a primary stress, or miscalculate SIFs, that can really hurt your elbow system. And it really, it doesn't give you a good picture if you're using wrong inputs in your analysis. So when should we analyze? What are Maverick's internal rules for when we would say a formal analysis is required? Some systems are so basic that you can just throw in an anchor here, a guide support here, a couple dead weight supports there. To us, when we see a system over 50 PSI and significant temperature swing, that would tell us it's something that you might want a formal analysis for. NM2 does provide some guidance as well, but I'm just kind of sharing what Maverick does here. So if you have significant wind or seismic concerns or any kind of complicate or combinations of these design conditions would warrant a formal analysis. Or if you have a complex piping arrangement. So what do I mean by a complex piping arrangement? Well, FRP doesn't just carry water all the time. You carry harsh chemicals. So if you have something that is very critical, you're going to want a formal analysis. I would consider that system complex. If you have many fittings, if you have a lot of twists and turns, if you have large diameter and low stiffness, so that picture on the bottom right with larger diameter elbows with short offset lengths, that is pretty stiff. Even though FRP is flexible, that is a stiff system because of the large OD on that. So if you have limited natural stiffness in your routing, if you have a header with several branches coming off and a lot of thermal expansion, that's going to be a problem. Riser piping, it sounds weird to say that riser piping could make it complex, but if you have a long rise, that's a lot of thermal expansion that you have to direct somewhere. It lifts off supports, it binds up other supports, or it binds up elbows. So I consider riser piping pretty complex. This is our preferred method or our preferred layout for FRP pipe, is to have a flexible system of arrangement where you utilize the natural flexibility of FRP and offset lengths to absorb expansion at changes in direction. So you're going to put an anchor kind of mid-span to protect any fittings, just direct expansion to the elbows to allow for the flexibility of FRP to reduce those stresses. You would want restraints in all directions. Static analysis does not capture surge and fluid momentum effects. It does not know that when you turn on that pump, you get a pretty good slug going through there and knocking that elbow and shifting your pipe. So every change in direction needs some sort of a restraint. We don't like free floating systems where it's no anchors and just kind of slides everywhere. It looks great in your pipe stress software. In reality, not so much. This is the optimal arrangement for managing stresses, minimizing support reactions, so that it is preferred. The picture on the bottom right shows if you have room to do expansion loops to absorb expansion, if you have more of a long straight run that you need an expansion loop. But honestly, expansion loops are not always possible. They're expensive, they require more fittings, more space, more structures, more supports. It's not always possible, so sometimes you just need to go with the expansion joint solution. Not always preferred. You have to decide, do they need to be tied? Do they not need to be tied? I'll say expansion joints make a lot of sense on pump outlets to prevent vibration from pump being transferred to FRP because of the non-ductile nature of FRP failure. But expansion joints are not a one size fits all. Sometimes you have no other choice, you have to use them. If you have high pressure systems though, now all of a sudden you have an open end and you have to deal with that thrust. So that's why you have to decide, do you need tie rods or no? Hot and cold cases affect what your tie rod gaps need to be. And you need extra supports to do this. It's increased maintenance items, it's increased costs to do expansion joints. So it's not the first solution. An older method of supporting FRP pipe that is still sometimes used today in certain situations would be a restrained system. So basically you anchor each end and you protect the fittings, you keep the pipe in compression. It's fairly strong in compression, so this is really used for long straight runs. Rule of thumb, I would say, is somewhere around 300 foot between anchors. So let's say you had a 600 foot straight run of pipe, you might need 3 anchors in that run. Now, I should say that that middle anchor in your pipe stress software will show up with very low loads because it's balanced from the anchors on the outside. That is not really the case. If it's not installed perfectly in line, if the shear collars have a little bit of a gap in it, if there's a little bit of flexibility in your structures, you're going to share a little bit more of that load. So don't trust an anchor that shows 0 load in a restrained system. But you should know also that when you do a restrained system and you have any kind of temperature, you're going to be dealing with a lot of thermal force, whether it's from expansion or contraction. So it sounds really good in theory, and then when I present a customer with a 50,000 pound load that they need to design their structure for, that's 30 feet in the air, then they decide that maybe an expansion loop or expansion joint is actually the way to go. Okay, stresses are managed, everything's optimized, you're all done, right? Well, not quite. What are you connecting to? What are the equipment loadings? Unfortunately, and this isn't just with FRP, but I'll say there's a disconnect between piping and equipment. Tank designers don't want to deal with pipe. Pipe designers don't usually want to deal with tanks. I'll say tank designers design their reinforcement pads on their vessels for their loads only. They do not want to take any more loads. They will say you need an expansion joint at every nozzle, and I'm sure some of you guys have dealt with that before. Well, I've already brought up the issue with expansion joints that it's not always the perfect solution. So that complicates matters a little bit, but you're talking about extra supports and extra cost. I'm going to talk more about this in a separate webinar, most likely, but I want to show this example just for awareness. So consider this example. We're just going to use 6-inch FRP pipe, pretty standard size, and we're going to consider temperature and deadweight loads. Pretty common arrangement. If we assume the anchors are rigid, which in Caesar, it'll be something 10 to the 12 pound per inch, very, very stiff. The stiffer the connection, it means it carries more load. So that moment there on that connection, if you give that to the equipment designer, they're gonna laugh at you and say you need an expansion joint. For the pipe stress analyst, they're gonna see 5,000 PSI stress and think it's horrible because the pipe is bound up. It has no flexibility to rotate around that connection point. So the inexperienced analyst is gonna require expansion joints or large repads on the tank. You're gonna have to have additional supports. Then you're also gonna need to manage that thrust as well. If you assume a reasonable stiffness. Now we've done studies on this. I'm not suggesting use 10 to the 4 across the board. Don't hear me say that. But usually 10 to the 4, 10 to the 5, 10 to the 6 gets in the reasonable magnitude for FRP. If you use a reasonable stiffness, your moment goes way down, your stress goes way down, about 8 times less, and I would say that's acceptable, all by using realistic assumptions. Are these rigid? The left pick, you can't see it, but it actually says do not walk on. So if you can't walk on it, I would venture a guess to say it's not very stiff. Smaller loads can present problems with these nozzles. It doesn't need to be a high load to cause concern. Even that 300 foot-pound, 400 foot-pound could be a problem on these nozzles. Just because the pipe stress is acceptable does not mean that the tank is okay. So we're going to transition now to talk about pipe support selection. We're still going to talk about pipe stress because there is some give and take there. So your analysis is complete. You have the support types defined. You know how your system needs to be optimized to run well. But what do we actually know about what pipe stress tells you about pipe stress? Well, this is what you're going to find out. Really, the only hoop stress you're going to find out is just from pressure alone, just basic cylinder equations. All of the rest are axial stresses, torsion stresses, some sort of combined axial stresses. And this makes sense because pipe stress software is one-dimensional. It's beam theory. It thinks the pipe stays perfectly round. Well, we know from slides before with low flexibility that that is not the case with FRP. So what doesn't pipe stress tell you about the actual stresses in the pipe? You're going to see a lot of these with hoop in them. A lot of the hoop bending stress, like I said, it doesn't oval in your pipe stress software, but it might in real life if you don't have the proper supports. And all of these other supports or all these other stresses you're seeing at supports in Caesar, in K-pipe, all of your supports are perfect. There's no extra stress. It is just based on beam theory alone. So now where's your confidence level that pipe stress can be done by anyone? Can you just throw in supports you find the quickest off the shelf? Selecting the right supports means just as much as performing the pipe stress. And I say this a lot, if you can design the best system in the world, but bad supports will absolutely negate it. Just a brief slide, just so you know some of the more common types of supports that you'll find in FRP systems. Slides, one-ways, guides, restrain it perpendicular to the pipe. Anchors are fixed points at direct expansion. And then there are other styles too that you can optimize your gaps if you need a little bit more flexibility, if you have more expansion in your system. You can base mount it, hang it. Riser piping often needs supports. If it's a pretty tall rise, sometimes you just need to flange mount it based on constraint issues or lack of room. I'm going to finish here with talking about the purpose of pipe supports, specifically for FRP. Why do they have to be special and not just off the shelf? The supports on the right are their Maverick supports. They look robust, maybe too much, some might say. I've heard somebody say they have been called boat anchors before. So why do they need to be as wide and stiff as they are? Well, one, you need to prevent point loading. Mentioned this a few times, non-ductile, brittle failure. You cannot point load a brittle material. And you also want to minimize abrasion. So you see in that bottom picture, you see the rubber line supports. You cannot put FRP in contact with steel. The steel will win when it wants to move. Here are some examples of point loading. The narrow supports will pinch the pipe. Take note of the wooden support. I'm going to come back to it a little bit later, or I'll at least reference it. The one on the right, it's a guide. So in stress analysis, you put a guide, you think it's the right support. Well, if you put the wrong guide in your system, you're point loading the pipe, you get some shear in the bottom, and ultimately you get a failure. If you have the wrong OD, if you have a support too close to a joint, now you're point loading the pipe again. If you have system movement, the picture on the right, obviously there was a shield there at one point, but improper restraint caused movement, probably shook off, walked off, and now your pipe is point loaded. It's not supported properly anymore. So just remember, FRP has a variety of ODs because of pressure ratings and strengths and properties. It's custom, it's great, but you have to understand how to deal with that. Steel is pretty easy. You know what you're getting. You know the ODs of a Schedule 40 steel pipe. Just look at one manufacturer's pipe. Their 14-inch pipe is 3/4 greater diameter than the 14-inch steel pipe. Another fabricator is even more than that, 7/8. So how often have you seen these types of supports to solve the problem? Instead of building it custom because they didn't think about supports quick enough and they just bought some off the shelf, well, they knew they couldn't go with the 14-inch support, so let's just go with the 16-inch support and have a huge gap and it's just improperly supported. So this is the realities. This is a research project we did that tells you why point loading is bad. Other than I can tell you all day long, I can show you failures, but this is the reality. This is the theory that goes into the reality. So this is a separate webinar. I just want to show you for illustrative purposes, but I modeled this in pipe stress software, and I also modeled this in FEA. What we want to do here is compare a 4-inch pipe with a shield, which is a picture on the right, or the shield walked off and the pipe is directly on the steel. The blue bar is Caesar. It's a perfect support, remember. The red is the point loaded directly on the steel, and then the green is having a shield for a 4-inch pipe. The main takeaway from this is we're looking at hoop stress here. Remember, pipe stress doesn't really tell us what hoop stress is, at least when it comes to bending. So Caesar thinks it's 0 when you're just looking at dead weight because it's a perfect support, whereas that pipe directly on steel is already carrying 622 PSI of stress. When you add pressure, the reality for this support is that it's 40% higher for a dead weight plus pressure case if you put that pipe directly on steel. If you have a proper support, the stresses increase, I would say, negligibly. Nothing is really perfect as theory would predict. So hopefully point loading is clear to the viewers here. Now supports need to do what they're supposed to do. They need to support the pipe without stressing the pipe. Seems simple enough, right? So another investigation, pipe stress versus FEA. So whereas the previous one showed 4-inch pipe, we're okay with shields for 4-inch pipe because it's a stiffer profile, smaller diameter. Well, what happens when you get to 18-inch pipe? That's a little bit more flexible. You have a different diameter to thickness ratio. So I wanted to look at this to understand why. I would say, well, Maverick's catalog stops at 12-inch. We don't really want shields on larger pipe or duct without further evaluation. Shields, again, for 4-inch, okay. For 18-inch, not so much. And you might be asking yourself, well, why does it matter? Steel is very strong. We've already talked about it being stiffer and stronger than FRP. Why do we need wider supports? Why do we need a full cradle? Why do we need full clamps? Would you expect to see any notable differences between these two types? Well, I wouldn't show them if there wasn't a notable difference, so let's look at it. Again, blue is Caesar. The red is just using the shield, which in this case is the improper support for the larger diameter pipe. And then the green is having what we would say is a more proper, a cradle, a full support underneath the lower 180 of the pipe. So this is the hoop stress. Again, hoop stress, pipe stress doesn't tell you, in the pipe at the saddle horns. The saddle horns are the sides of the pipe. So in our case on the shield, it's basically at the edge of the shield where it's trying to egg shape an oval and stress over that line there. Remember that wood cradle support I mentioned before? That's a classic example of saddle horn stress failure because of poor supports. In that case, it was because it was too narrow, not because it wasn't fully supported underneath. But just look at what happens when you add pressure on the chart on the right there. That pressure stress, the 2663 in Caesar, that's just PD over 2T, cylinder equations. The reality, if you have a shield, it's double that. I would say that's excessive. I would say that's overly allowable, but you would never know it. So do you trust the pipe stress results just blindly? If you're putting bad supports in your system, you're invalidating the pipe stress completely. The job of supports should not be to add stress to the pipe. It needs to keep the pipe round. Finally, the purpose of pipe supports is to ensure proper restraint and system functionality. The bottom line, it has to restrain the pipe how the pipe stress asks it to. You need to make shear collars are installed and engaged properly. You need to make sure that the gaps are set because the gaps are critical to system functionality. The system needs to operate reliably, predictably, and as intended. So which one of these supports best satisfies the pipe stress requirements? The one that deflects an inch when it's loaded, or the one that is very stiff, good shear collar on top, not deflecting at all, not pinching the pipe? How do you think, aside from maybe pinching the pipe because it's rotating there, how do you think the elbows feel next to this pipe at the bottom of that rise? How do you think it feels about deflecting 1 inch more than it was supposed to? I'd venture a guess it's a lot higher stress than what was predicted. Wouldn't be surprised to see some failures in that pipe over time. Which one of these will keep the pipe round? The support on the left looks okay from afar. You have stiffeners or you have rings around that clamp there. Well, There are some failures on this one because it was not the proper support for the loads. It ended up failing the steel, which is very hard to do. What is it doing to the pipe as it's trying to oval now? The steel isn't doing much, so now the clamp is just kind of flexing in there and it's pinching the pipe. Or you could have good, solid, stiff, wide, robust supports, keeping it round. So you might be saying, I have good supports. They're wide, they're stiff. Well, again, keep in mind, pipe stress is static. It does not know of your system dynamics. So my rule of thumb is 3 consecutive hangers is not good because hangers have 0 friction. I would say don't do more than 2 hangers in a row. It just does not work well. You need that little friction from a base support to prevent kind of vibration and moving back and forth. You say here, okay, I got guides, U-bolts. I don't have shields, which I should, but at least I have a guide. That's what pipe stress said I needed. Well, look at that trapeze hanger. I would say that's not very stiff. So guides with poor structures are not going to guide the pipe. They're just going to sway. So what happens because of these types of pictures? Well, the support's going to end up walking off if you have too much dynamics in your system that aren't considered. If you don't have proper shear collars installed, if you have consecutive hangers, flexible structures. The one on the left moved about 3 feet. The one on the right shifted off the steel and is never coming back because you can see it's below the steel. It's never going to make it back. So now you just doubled your span right there. So look for signs of excessive deflection. Movement is okay as long as it's predictable and not constant, not to fatigue your system. Large displacements and unpredicted movement will fatigue that system, which when you say fatigue to an FRP guy, it usually means shorter life because of our non-ductile material. If you see paint 6 inches away from a hand railing, I would say you have at least 6 inches of deflection in that system. If you busted up your steel because of a surge event, I would say you don't have enough anchors in your system. So kind of wrapping it up here, communication is key. You will not get what you need unless it's correctly designed, defined, communicated. That goes for support types, loads, reinforcements. You need to talk with the tank manufacturer. You need to understand what you're connecting to. You cannot just design a pipe system in isolation. You can't just stay within your box. You have to understand the full picture. You need to understand what the steel looks like, what kind of supports are going to be used, what you're connecting to. Properties vary depending on construction method and from manufacturer to manufacturer. We showed several slides with that. I hope that's kind of made sense with you guys. So get good data. Don't assume. NM2 and 3 can certainly help, but it's not everything. It's going to be conservative, and you have other manufacturers who don't want you to use NM3 values. They want you to use theirs because they've done extensive testing. Understand that steel principles cannot be directly applied to FRP. If nothing else, buy NM2 and read it. Read it for the design section. It is so much better than B31.1 and B31.3 for our North American people. Just read it. You will learn so much about analyzing FRP that has been tribal knowledge in the past. Understand what pipe stress software does for you and what it doesn't. This isn't just an FRP versus steel issue. It is more pronounced with FRP because of our failure mode, but the stresses, they still tell you the same stress for a steel system as they do for an FRP system. So understand what it does and what it doesn't. What are the gaps? Unrealistic assumptions will have significant costs. I don't even want to say can. It should say will. If you have too high design conditions, well, your pipe thickness just increased. If you don't have realistic assumptions for your nozzle stiffness, well, you just added expansion joints. You might have added overwraps, reinforcements, increased thickness on the tank reinforcement pad. So understand that unrealistic assumptions will have cost impacts. Understand the differences between theory and real world. We just talked about that. Hopefully you remember, you don't want consecutive hangers. Everything looks great. You need anchors. You can't just have it free floating. It might look great in your pipe stress software. In reality, now you're walking off steel, your clamps are shifting, and you're point loading the pipe. Poor support selection will ultimately reduce the life of your systems. That should be pretty obvious from the pictures I showed here. The perfect analysis will most certainly be invalidated by bad supports. The supports need to be wide, they need to be stiff, they need to be made for FRP. With that, that's all I have. Now we've come to the question and answer portion of the webinar. I cannot promise I'll answer all of your questions to your satisfaction, but I'll be as honest and straightforward as I can. If I don't know the answer, I will look into it and I'll get back to you. So Tom, you can chime in now, and why don't you start us off with some questions?
Okay, we do have a few questions, Daryl. The first question that I have right now is, what is a good theoretical laminate analysis software?
Sure, that is a good question. There is Trilam, and I'm not sure who asked it, if this was kind of a leading question and wanted me to say that Trilam is unsupported and has some issues and the person who developed it is no longer around. That is certainly a problem, but throughout the industry, Trilam is the most common laminate analysis program, at least in the corrosion industry. There are others. There's Composite Pro, VectorPly. We use FEMAP for our FEA software, and it has a laminate builder built in. So that will actually give you very similar properties to what you get in Trilam or the other software. The ASME NM2, RTP1, Section 10, they all have the classical laminate theory and micromechanics. So if you were a glutton for punishment like I am, you could do a MathCAD and have a 40-page document to kind of duplicate what stress analysis or laminate analysis calculates. But there are several options out there.
Okay, good. Next question, is the laminate analysis a progressive failure analysis or a first ply failure analysis?
Oh, brother, this gets filed in the, I'm not going to answer it to your satisfaction. So I mean, this is very, very into the weeds for very, very smart and technical people who really understand laminate analysis. I'm claiming to be maybe in the middle range of not knowing anything and knowing everything. To me, first ply is bad. If you fail that first ply, it's usually that inner layer. It's usually the weakest one, which is the very inner layer that has the highest resin content, which means lowest reinforcement. So you start failing that because you're overstressed. Well, now you're letting the chemical permeate, penetrate, migrate into your laminate. So I don't really put much stock in progressive failure, which means kind of, I would say, unzipping a zipper kind of thing about it. You start and then keep going and it transfers load to the next strongest ply. I want to look at what's that first failure, and that's usually the veil on the inside.
Okay. The next question I have, Daryl, is if the pipe stress analysis analyzes axial stress, why would we use hoop stress intensification factors?
Ooh, good question. It's a pretty big topic and it's a little more theoretical, but I couldn't really go into it in the presentation, but I'm glad somebody asked. The reality is when you bend an elbow, the max stress is in the hoop direction. It's hoop bending stress. Currently, your code stress equations are only calculating axial direction stresses. So you have axial pressure stress and you have bending, or you have an F over A term, whatever, but it's only calculating axial stress. So if you're adding an axial direction SIF, your actual magnitude of stress is not reflective of what stress is actually in that pipe or in that elbow. So depending on the construction method, you might get a situation where you actually want to use hoop SIFs currently just to overcome the limitation in the code equations. I will say NM2 addresses this. Unfortunately, those using pipe stress software will tell me that there are no equations, there are no code stress equations currently from NM2 in this software. We are working on that. We have members of Intergraph on our committees. They are aware of our equations, where there will actually be a hoop stress equation to calculate the bending stress in the elbow. So you can use an axial SIF for axial code stress. You can use a hoop SIF for the code hoop stress. So it's pretty complicated, but just understand that when you bend an elbow, the max stress is in the hoop direction, but Caesar only tells you axial stresses, so you have to kind of make up that gap.
Seems logical. The next couple of questions we have, Daryl, relate to stress intensification factors, also SIFs. And the first of the questions is just, what is a stress intensification factor? What is an SIF?
Sure. So when you bend a straight piece of pipe, it stays pretty circular. There's no geometrical discontinuities. It's just a straight piece of pipe that you're bending. When you bend an elbow, it's different. It's a different element. It's a smooth sweep. It's not straight piece of pipe. It's going to have concentrations in certain areas. There are going to be some stress risers. When you have a T, for example, well, you're cutting a portion out of that T, and that's where some pressure stress multipliers come in to make up for that, which I haven't really talked about here. That's more for pressure design. But you have complex arrangements, and the pipe stress software, like I said, is only one dimensional. So it's basically a bar element in pipe stress, and you apply the parameters of diameter and thickness, but to pipe stress, it's still a straight bar. Well, that's not reality. So the SIFs are meant to be multipliers for stress to account for those geometrical differences that pipe stress inherently does not account for.
Okay. And the follow-up question to that was, can manufacturers of fiberglass piping provide stress intensification factors for their equipment?
Yeah, most certainly. The ones that do it the most, the one that have a lot of technical expertise in-house, they have that. You can look at their literature, they would happily supply it. Now, keeping in mind, this is for standard product, so it's easy if they have one standard product, then you can calculate it. We often work with manufacturers who might not have that expertise, might not have NM2 or BS 7159 or ISO 14692, and we'll work with them on their product line to give them SIFs, because an owner is going to go to their EPC. EPC has to do the analysis. EPC doesn't know about FRP. They say, okay, I'm going to go to the FRP guy for this data. So it's common for them to ask the FRP manufacturers for this data. I would say it's about half, maybe less than half, who actually have that data, but it can all be calculated, and it's not very difficult. You just need to know theory. You need to have the references. You need to be able to understand how to do the equations.
Okay. Following on the heels of that one, here's a question. Since the FRP piping properties vary across manufacturers and construction methods, how does an analyst perform the analysis if the owner is not willing to select a manufacturer of the fiberglass piping prior to the analysis needing to take place?
Sure, well, that's that $1 million question. And before NM2 came about, it's all on assumptions. That's where, I mean, we at Maverick only do FRP. So we know what assumptions are conservative and which ones aren't. Like I was saying, a low modulus may not be the most conservative assumption for your pipe stress, because it's going to be a more flexible system. You're not going to see as many stresses, or not going to see as elevated stress in your pipe. So that is a common gripe among engineers, because you're trying to get ahead of the game, analyze the system, understand what your routing needs to be, where your supports need to be. You might not care about getting the manufacturer involved yet. So I get that. And that was the purpose of NM2, or one of the purposes of NM2 and NM3, was to get a library of data that this group, a bunch of industry experts, come together and decide, okay, they can use these values if they don't know anything else. Now, I will say that's not perfect, that it's something, it gets them started, but then all of a sudden when you engage one of these manufacturers who've done a lot of testing, then unfortunately they might say, well, if you use these properties, I'll sell you cheaper pipe because I don't have to change anything, but it means you have to go back to the analysis. So it's kind of that iterative step where I would say you need to do the initial engineering, front-end engineering, snuff out all the issues you can with good assumptions, and then eventually you may still need to revisit that based on whatever manufacturer is selected.
Okay. Next question. How do you account for pressure thrust load from expansion joints in the FRP piping when the thermal expansion loads are also present?
Very good question. I don't know who's asking this, but I don't know if they're trying to prod me into getting on my soapbox here. Um, I have always considered expansion joints as a necessary evil, and expansion joint manufacturers hate when I say that because, right, that is a problem. If you have, let's say, a filled arch expansion joint in a slurry system, well, that is very stiff. It's about 4 times stiffer than an open arch expansion joint. So it takes a lot more activation force to be able to start compressing it. But on the other hand, you're also thrusting the opposite way, trying to blow out the expansion joint. So in a lot of pressure systems, I'll just be honest and say expansion joints are not really going to help you all that much. Maybe for a little bit of isolation of decoupling your system, maybe a little offset forgiveness, although or expansion joint manufacturers will tell you you should not be using it for offset tolerances. The reality is it can make up for some, but yeah, in pressure piping systems, expansion joints are very difficult because it's not a one, you don't just throw it in there and it solves your problem. There are thrust forces and right, there are counteracting thermal forces that need to be paid attention to. And further, usually when you have thrust forces that you're trying to manage, you might throw tie rods in there. Well, now, what if you have a cold event? Well, your tie rods just basically made that pipe a straight piece of pipe again. It can only compress. But if you have a cold case, your straight piece of pipe, now you just made a restrained system. It's not a flexible system anymore. So it can often bring more problems than answers it will solve. And that's just the unfortunate way. And like I said, I don't know if somebody prodded me with that, knowing that I've kind of given this soapbox before, but to me, that's just the reality. The expansion joints are necessary evils around pumps. Absolutely put them. You don't want vibration transferring into the FRP. It's just not going to work. There are some low vibration pumps. I know we've dealt with those before, but by and large, that's a great location for expansion joints. Low pressure ducting, certain high thermal expansion applications, things like that.
Very good. We're starting to run down on questions. Here's one though. How do you address the situations when you have completed your stress analysis and when they go to install the supports in the field, they have to relocate a support a few inches, a few feet here or there? Do you reanalyze? Do you re-perform the stress analysis, or is there a general rule of thumb how far you can move a support from the analysis?
Yeah, it's hard to say a rule of thumb, but that is a good question because we encounter it too. Um, the experience of the analyst matters. The sensitivity of the system matters. If you just asked me, I would say plus or minus 6 inches, not that big a deal. There are certain situations where it actually is, but that's for the analyst to kind of weigh. If you're getting into the feet, then I mean, either way, you need to convey that to the analyst. They're the engineer of record, so they need to weigh in on if it is a big deal or not. The reality is supports can be pretty wide, so that might take up some of that plus or minus in your kind of where the support is in your theoretical analysis, where it's just 1 point, or is it a 12-inch wide support that gives you a little bit more freedom to make that decision. But the the straight answer is you just got to ask the analyst. In my mind, plus or minus 3, plus or minus 6 is not that big a deal, but it really is system by system and how sensitive the stresses are. There are definitely situations where that will put stresses over 100% of the allowable, and that just tells you you have a very sensitive system and you might need to think about overwraps in that case. if they can't move the support back.
Sure, that makes sense, Joe. We have a few more questions, but let's try to get one more in, and then we'll have to answer the rest of your questions offline. We
Okay.
have all your questions in your emails, and we can reply to them via email. So the last question I want to try to propose to you is, do you have a specific generic conservative value for compressive strength when you use rigid pipe supports that clamp down on the pipe in
These
regards to
are
how tight we support?
These are outstanding questions, and I have a feeling people are just trying to get me to spout off on things and opine. I'm happy to do it. Short answer is no. I do not. There are compressive strength values in NM3. There has been much discussion, and this goes back 30 years, and I am not that old, so it is before I started talking about this. But we talked about the different construction methods of pipe, type 1, type 2, type 3. Some will tell you that the compressive strength either goes down or goes up, depending on what construction method you use. The kind of general philosophy throughout kind of the whole pipe stress analysis with FRP is to consider it's fine to consider it the same as a tensile strength. Whether it is a completely different question and answer that we are trying to, there is another ASME discussion actually talking about this right now to figure out what's the reality. ASTM D695 is a compressive test, but you're only testing a coupon. Is that the same as testing a full pipe section? So we want to figure out a way to test a pipe section, but you're somewhat limited with the load you can apply to a whole pipe section because it's pretty strong and it's very hard to get it to failure. So there are some limitations with that. There are some that say the modulus goes down when you put it in compression in a restrained system, which a lower modulus reduces your anchor loads, which is great. But if you're not 100% sure that that is always the case, then that's a pretty big leap to make. Because I would argue if you have a highly loaded anchor and structure that maybe has a little bit of stiffness, maybe that structure is rotating a little bit. Maybe it's flexing a little bit, which is reducing that load, which makes it look like it's a reduced modulus, when in reality, it's just a poorly designed structure, or it's not, the structure isn't designed stiff enough. So I can't answer the question. There's not one value. Whoever this is, we can talk. I'd be happy to kind of engage with you and see kind of your background and understand what you're trying to get. And maybe I can illuminate you with some of the ASME studies that we're doing.
Okay, that's it, Daryl. Why don't you tee off the next Maverick webinar?
Okay. Thank you for the questions. They're actually very good questions. So we are doing these about once a month. We don't have a date. We're targeting mid-September. I'd be really excited for you to join us. The next one will be given by Jeff Eisenman. He is the godfather of FRP and the president of Maverick, and just about everybody knows Jeff, and he's been around forever and has more information. He's forgotten more about FRP than I know. He's going to talk about a condition assessment of sulfuric acid piping by material testing. A lot can be learned from a single spool taken out of service. Send it to our lab, we'll look at it. He'll discuss the benefits of doing material testing, including confirming the resin, evaluating permeation and integrity of structural layers, glass corrosion, as well as confirming the corrosion barrier integrity of the laminate. So really, I hope you can join us for that one next month. But finally, that's it. I really appreciate your attendance. I truly hope it was beneficial. Feel free to reach out if you'd like to discuss anything, if you thought something didn't quite make sense, if you thought it was a little vague and you'd like me to clarify, I'd be more than happy to talk through any of these slides and just talk through any of your questions. So really, thanks again and have a good day.